Hi everyone, my name is Srinivas. Today we are here to present our project Exploring OS Scheduling Algorithms through Simulation. Today's presenters are Kiran, Sumith, and Srinivas. In the context of operating system, the efficient allocation of resources stand as an important aspect of system performance and user satisfaction. Process scheduling algorithms are designed to govern the allocation of CPU time among processes. Our project aims to provide a comprehensive platform for studying and evaluating various scheduling algorithms. The CPU scheduling algorithms that we worked on are mixed priority and round robin algorithm, also known as mixed PIRR. And the second algorithm that we worked on is priority based dynamic round robin, also known as PBDRR algorithm. Here is the first algorithm that we worked on. It is mixed PIRR algorithm. It is a novel CPU scheduling algorithm that combines features of priority and round robin algorithms. The purpose of this CPU scheduling algorithm is to overcome limitations of existing algorithms, addressing waiting time, response time, and system throughput. The round robin algorithm does not consider the importance and significance of processes. It simply solves the queue, so the process order that CPU performs cause a decrease in CPU efficiency. The priority algorithm has also some disadvantages because it solves the process priority for which process comes first. So it performs the process with the highest priority and does not consider the arrival time or the size of the process. The mixed priority and round robin algorithm is an algorithm that obtains the optimal advantages of both priority and round robin algorithms. Next slide. Here is a flowchart of mixed PIRR flowchart algorithm. So when at the beginning, the algorithm adds all the process in the ready queue, and then each process is assigned a priority level based on whether it is a static process or a dynamic process. Later, time quantum is defined by the algorithm. Here, time quantum refers to the maximum time for each process that can be run on the RAM before it is swapped out of CPU. Next, the processes are arranged based on the priority. If the current process has the highest priority, then it is placed in front of the queue. Then the time quantum, if the process does not have the highest priority or if its burst time is greater than the time quantum, it is allowed to execute for the duration of the time quantum. Next, the algorithm checks whether burst time is greater or time quantum is greater. If the burst time is less than time quantum, the process will can finish its execution. If the current process can complete within a time quantum, it is allowed to run to the completion. Otherwise, it will be swapped. Next, the change of process priority to the lowest priority in the queue. After a process has executed, whether it is fully executed or partially executed, its priority is adjusted to the lowest in the queue to give a chance to other process. After this, the algorithm checks for the count. Here, the count refers to redundancy column, which is likely the count of how many times a process has been executed in the given CPU time. If this count is less than 3, the process can be considered for execution again. Af- After the after this, once the process has finished executing, it is terminated and removed from the queue. At the end, the scheduling algorithm ends uh, when all processes have been cleared out of the queue. This process repeats until every process that has been scheduled has been moved out of the queue. Now, my teammate Sumit will continue the presentation.
Thank you, Srinivas. So I'll be explaining about priority-based dynamic round robin, which also considers the fact of priority algorithm and the traditional round robin algorithm. Therefore, limiting, therefore avoiding limitations that are usually present in scheduling algorithms. So this particular algorithm was implemented on a real-time systems. So there are two types of real-time systems. One is soft real-time systems and firm real-time systems. This algorithm was particularly implemented in soft real-time systems, where the failure to meet a deadline can result in performance degradation. Some of its applications are they are used in ATM, railway, and flight reservation. So the main concept in revolved around this algorithm is intelligent time slicing. Intelligent time slicing is a way of allocating time quantum to each process that is involved in the algorithm. So it considers various facts. For example, it considers original time slicing, also known as OTS. So this is the base time slice allocated to a process without special condition, and also it consider a priority component whose value is either 0 or 1, and the shortness component. This evaluates the difference in burst time between the current and predecessor process. So our research addresses the need for a more efficient algorithm. Hence, this hybrid algorithms um, in the process list, if say for example, if there is a long process and a short process, so if the algorithm considers to eliminate the short process at the starting, we can see a 25% reduction in average waiting time and turnaround time, and also reduction in context switching. So and that is why this particular algorithm stands out when you compare with a traditional round robin algorithm. So further, to evaluate our algorithm, we conducted a series of experiments uh, comparing PBDRR against the modified round robin algorithm. We focused on metrics such as average waiting time and turnaround time, and the number of context switches using a simulated environment with varied process loads and priorities. So it was indicated in the paper that when this particular algorithm was implemented on the soft real-time system, so it resulted in 25% reduction in average waiting time and also 40% reduction in context switches. So in conclusion, I would like to tell that the PBDRR algorithm offers a promising approach to scheduling algorithm in soft real-time system. So this is a pseudocode that is used in the uh, that was used in the implementation of algorithm. Um, so further, um, my teammate Kiran will continue with the results of our project and also the demonstration.
Thank you, Srinivas and Sumith, for explaining the algorithms. So let's look into the methodology. The simulator initiates, the simulator which we have developed initiates by capturing the essential inputs, where the inputs are like the number of CPUs, input output specification, arrival time, and the priority level. This input variables are then processed through the designated algorithms. Here, for coding, we have used the Python, and for developing of the web application, we use the Flask, and where we have written all the algorithms, and these designated inputs which we are going to feed, it will go into the designated algorithm. Then the simulator will generate the visual representation of the results, where we have used the Gantt charts and the bar charts, which gives us a clear comparison between the different algorithms for the different inputs that we fed. And the conclusive output is also presented through a tabular format, which contains the critical parameters such as arrival time, total burst time, completion time, turnaround time, waiting time, and the response time. So let's look into the results. Let me go and show the demo of our application which we have developed. So this is our application. So we use the Flask to develop this application, and we can see that these are the inputs that we are feeding for the algorithm. We have the quantum time, process ID, burst time, arrival time, priority, and repeat count. So here we can customize our inputs where we can give different values, and we have the samples. These are the samples that we have taken from the papers, and we have compared it, the results. And here in the custom inputs, we can add the inputs over here by typing, and then we can add another process and keep on adding it, and when we click on the schedule, we can see the results. Let's go into the sample one and see the results. So this is the sample one, so where we have the quantum is 4, and these are the input values that we had given: the process, burst time, arrival time, priorities, and the repeat counts. So when we look into that, we have a tabular representation of the results of the all the algorithms here. Like we have a different tabular representation for each of the algorithms. We can see mix PIRR for each process, what's the waiting time, what's the turnaround time, and for each of this algorithm we have we have an chart, a bar chart, where we can see the comparison between the turnaround time and the waiting time. So we can see at a different process level what is the outputs over here, and it is the same thing for all the other algorithms. And at the end we can see the total comparison between all 4 algorithms, that's round robin, mixed PIPR, PBDRR, and first come first serve. So where we have compared the average waiting time and average turnaround time for all the processor for each of the algorithms, and we can see that the round robin algorithm has taken more waiting time and turnaround time compared to any other algorithms that we have used. And the best algorithm is the PBDRR, which has the very less average waiting time and average turnaround time. So we can route back to our home page, and this is for the sample one. We have other samples, like we can go into the sample 6. We have a huge set of data here, so where we can see for each of the algorithm we are getting the huge set of data, and we can see the comparison of the turnaround time and the waiting time in the graphs. And in the similar way we can see the results for all the other algorithms over there, and we can see the comparison here. And here also we can notice that the PBDRR has the best average time and the average turnaround time. And this data, all the samples has been given in the backend in the CSV file. So when we compared our results after implementing the algorithms with that of the results that were mentioned in the paper, we were able to reach around 90% of accuracy with the results, so which gives us the PBDRR is one of the best result. So these are some of the charts that we have taken from our application. So mixed PIPR and PBDR algorithms were implemented for various datasets, and we have checked various scenarios by giving the different inputs, and we had a thorough comparison of all these algorithms with the round robin and first come first serve. Analysis of PIRR and PBDR algorithms with a traditional round robin and first come first serve indicates that a hybrid of round robin and priority algorithm is more efficient when we compare it to the already existing traditional algorithms. So we know that no algorithm is ideal in every circumstances, so it is impossible to watch a precise scheduling algorithm in action, yet precise performance can be viewed in real-time operating system operations. So several elements such as changeable capacity have a substantial impact on performance. So we can conclude that the hybrid algorithm performance is better than that of the traditional algorithms, where it combines the priority and the round robin. Thank you.